Welcome to the second video of the first chapter of Crystal Clear Electronics 2. In this part, we will learn about the components of the CPU, how they work, and the types of registers.
The CPU, or Central Processing Unit, refers to the unit responsible for performing all the operations necessary for functioning. Think about the CPU as the brain of the computer. This unit is capable of performing specific instructions on different kinds of data, and these instructions can vary from architecture to architecture. We can talk about microprocessors since the functions of the CPU were implemented on a single silicon-based integrated circuit. The microprocessor always performs the role of the CPU, but in each case, we are talking about a physical component, which may contain several modules, for example a graphics processing unit, a sound card, and so on. It follows that while in the case of a microprocessor, we can use the term CPU as a quasi-synonym, as we will do, this would not be correct in the opposite case. With the introduction of transistors, large electron tubes could be replaced, and with the miniaturization of transistors, it became possible for engineers to create more and more complex architectures with smaller dimensions but higher computing power.
We've already talked about the microprocessor integrating all the functions that it needs to perform as the brain of the computer. But where exactly are they integrated?
In this case, the integration means that you can find the circuits that make up the CPU on a single wafer, conveniently a silicon semiconductor wafer, rather than as separate components.
Earlier, germanium had been used as a semiconductor, but the appearance of the first silicon-based integrated circuit was critical to the development of the CPUs. In the 1960s, 4 transistors were successfully integrated on a single silicon wafer, Fairchild semiconductor, which was a huge improvement on germanium in terms of manufacturing cost, quality, and stability, opening the way to complex integrated circuits.
The first low-complexity integrated circuits were already intended for complex tasks, such as the Minuteman rockets or the Apollo program's computers for inertial calculations. The technological improvement in these projects was extraordinary, both in terms of the expertise, vocation, and financial investment involved, and the results were circuits with even higher levels of integration. The first microprocessor, in the modern sense, was introduced in 1971, the Intel 4004 processor, which had a 4-bit architecture, that is 4-bit word size, and an instruction set consisting of addition and subtraction. Let's face it, it's not much, but it was a pioneer in the industry.
The sophistication of processors is not necessarily proportional to their internal word size, but longer word sizes typically result in higher computing power. Today, 8-bit microprocessors are still in use, but 32 or 64-bit versions have become more popular in general. It is more and more likely that microprocessors with even longer word sizes will be used in the future.
And now, let's look at what units make up a microprocessor and how they are built. This is illustrated in the diagram, which is a simplified illustration of the internal structure of a CPU, showing only the major components. Now we will spend a few minutes talking about this figure. Understanding it will help you a lot in your engineering career. Registers are fast, small storage units of the processor for temporary data storage. They can be considered as an integrated part of the processor as read-write memory. There are general-purpose registers, whose function is determined by the instruction currently executed by the processor, and special function registers, which always perform a given task. A processor can have many thousands of registers, and this number increases with the complexity of the processor. Their importance is unquestionable for elementary operations such as addition. We store the numbers to be added in registers.
A couple of special function registers are worth describing separately too. The instruction register, or IR, contains the instruction, its binary code, that is currently being decoded and executed. An instruction is information stored in binary format that tells the processor what data to process and what operation to perform. Instructions are always specific to a particular processor and are executed in several steps: fetch, decode, read operands, execute the instructions, and store the result. Depending on their type, they can be data and memory management, arithmetic logic unit or ALU control, program flow control, or processing unit state control instructions.
The next register we will look at is the program counter, known as PC for short. The value of the program counter register contains the address of the next instruction to be executed in the program memory. Certain instructions, typically jump instructions, modify the value of this register to cause the program execution to jump to the correct location at every if-else branch. This depends only on the value of the PC register. When debugging, you can tell exactly by its value which instruction the program is working on. Think about this when you are in a programming environment and you have just stopped the program to look at the value of the variables.
The abbreviation SP stands for stack pointer, which is basically a memory address register that points to a specific location in memory. To understand why it exists, we first need to clarify the concept of the stack. The stack is the part of memory that is used by a function when the program is running and in which the function can store its own local variables. The exact position of the processor in this stack during execution is determined by the value of the SP, all of which you will learn more about in Chapter 3.
PSW, or Program Status Word, is a register in which the processor provides feedback about its internal state, which can be used by any instruction. We should think of such data as the bit indicating overflow that is generated in the wrong case when an instruction is executed.
The memory address register, or MAR for short, is used to access data and instructions from an external memory attached to the processor during the instruction execution phase. It contains the memory address from which the processor reads or where it writes the data. The memory data register, or memory buffer register, also known as the MDR or MBR, is where the data is located, which is to be written to or read from the external memory that is connected to the processor.
In addition to special registers, there are also general-purpose registers. Let's look at an example to understand them. Let's assume that we allocate space somewhere in the memory for 3 variables and give them the following initial values: a equals 0, b equals 3, and c equals 5. At some point during the execution, the microprocessor must perform the following simple addition: c equals a plus b. The general-purpose registers may have different names in different processors, but for now, we'll call them R1, R2, and so on. Instructions, including addition, using the general-purpose registers in an instruction-specific way. This is defined in a way that is specific to the instruction. For example, for a given architecture, the processor can go through the following steps. First, it copies the value of the variable a from memory to the general-purpose register R1, then variable b is copied to R2. Next, it performs the addition, and the result is written to the general register R1. Finally, it writes the value of the general-purpose register R1 to the location of the variable c in memory. It's clear that general-purpose registers are essential components of the microprocessors used to execute instructions. It is important to point out that all instructions that use general-purpose registers work in a similar way to this.
Now let's move on to the presentation of the ALU. The CPU has an execution unit, the ALU, which stands for the arithmetic and logic unit. This separate unit performs arithmetic or computational tasks such as addition, subtraction, multiplication, and division. Moreover, the ALU is responsible for logic operations such as logic AND, OR, XOR, and bitwise operations. As we mentioned earlier, it can perform these operations on n-bit numbers corresponding to the word size of the processor.
The following figure shows an abstract representation of the execution unit. Let's interpret the inputs and outputs. A and B, they are operands on which the given operation is executed by the unit. R, the result as the output. F indicates the control signal, for example, to select the appropriate operation. Finally, D, the status output, overflow, parity, and so on.
We have already talked about how the separate parts of the CPU work. Still, you need a controller that connects them, which can convert the instructions from the code into instructions that can be executed by the parts of the microcontroller.
The control unit receives the clock signal from an external source, reads the next instruction from the address corresponding to the content of the program counter register, and then immediately increments the value of the program counter. The control unit is responsible for decoding the instruction, updating the contents of the registers, and selecting the appropriate operation for the ALU as well. It also updates the stack register on various jump instructions. For example, when we call a function from our code, the input parameters of the function and the address to jump back to after the function is executed are all written to the stack, so the stack is getting deeper.
A general scheme for the processor instruction execution, that is, the sequence that the control unit executes for each new instruction, is the following: reading a command from the program memory, decoding, updating operands in the registers so that the ALU can access them, execution, storing the result. This sequence consists of 5 phases. Each phase takes generally 1 clock signal of time, so the instruction takes 5 clock signals of time to execute.
Modern microprocessors use similar sequences, but there is a twist in the story. Modern architectures now use a so-called pipeline computing, where the control unit can control the execution of multiple instructions in parallel. In the figure showing the pipeline instruction execution, the successive instructions and their phases are shown in horizontal lines. Each phase takes 1 clock signal to finish. Only one of each type of phase is executed at a time, but there are times when the processor is executing more than 1 instruction at a time, so, overall, our calculations will finish faster and the processor will be perceived as faster by the user.
This can only be the case if you know the next n instructions in advance, and they can be loaded into the pipeline in parallel without dependencies. This is not always the case, and there are various stages for avoiding these situations, but we won't discuss them in detail in this curriculum. Generally speaking, the control unit is responsible for providing data flow, synchronization between the components, timing, and control of the input and output units.
Let's move on. The internal wiring of the CPU, also known as the internal buses, allows communication between the components just described. What you need to know about system buses in a few words is that they are used to connect the different units of the computer. Their job is to transfer information from one unit to another as quickly as possible. These connections are basically used to transfer 3 types of information: data, address, and control signals. The information on the bus is used to synchronize the different components and to gain the functionality of the whole system. Most importantly, not only the memory and the processor, but also the various output and input units, the peripherals, are connected to this bus.
We are still talking about several separate physical components, but step by step we have arrived at a complex system that can work independently. Stay tuned for the next video of this chapter, where we'll look at the microcontrollers, summarizing what we have learned so far. Bye!
Bye bye!